Hey everybody, this video is about static equilibrium, so let me define that for you. Let's say there's a stick and you just throw it in the air. So you throw a stick in the air and then it's tumbling through the air like this. Okay, now the center of mass of the stick, let's say it's moving like this. Right, the velocity of the center of mass. And then also it's rotating, right? It's rotating, rotating, rotating. So that's the angular velocity. Angular velocity. Okay, so if you sum forces, mass times acceleration, if the velocity of the center of mass is constant, then that means the acceleration is zero, right? Zero. Because acceleration is the time derivative of velocity. So if the velocity is constant, the time derivative of a constant is zero. Right? So effectively, sum all the forces acting on that stick, it's zero. Also, if you sum torque, right, it's I alpha, moment of inertia, times angular acceleration. Now, if the angular velocity is also constant, if the angular velocity is constant, then the angular acceleration would be zero, right? Because angular acceleration is the time derivative of angular velocity. If this is constant, then the angular acceleration is zero. Okay, so this is called equilibrium. To be precise, it's called dynamic equilibrium, but you can just say equilibrium, and it's implied dynamic equilibrium. Right, so some forces equal zero, some torques equal zero. Now, a further constraint, if the stick is just sitting there, not moving at all, then also the momentum is mass times velocity, right? If it's just sitting there not moving, then the velocity is zero, which means the linear momentum is zero. And then it's also not rotating, right? So then the angular momentum, I omega, right? So this is moment of inertia, angular velocity. If it's not rotating at all, the angular velocity is zero. So then the angular momentum is also zero. So then if you have all four of these conditions, some forces equal zero, some torques equal zero, the linear momentum is zero, the angular momentum is zero. That's called static equilibrium. Okay, so that's it. It's like the world's shortest lecture, right? Okay, so let's just go through some examples where we use this. Okay, so here's an example straight out of the book. So there are these two strings supporting this weight over here. Okay, so we're trying to figure out which string is going to break, and then how much mass do you have to add for it to break, and then at most the strings can support, or each string can support that much weight. Okay, so what's the first thing we do? Free body diagram. Okay, so let's think about how we should do this. I'll draw the free body diagram of this pivot point right here, where these three strings join. So there's tension from this, I'll just call it tension 1 from this string. Tension 2, I'll just call it, for this string. And then there's this weight. I'll just call it mg for the weight. Okay, so there's our free body diagram. That's done. What do we do next? Pick coordinates. So I'm just going to pick coordinates maybe just like this. All right, so that's done. Now let's write out Newton's second law. Let's take a look at the geometry over here. Okay, so if this is some angle, I'll just call this theta 1, then that would be, like if you look at the picture, that's like this angle right here, which is the same as this angle right here. And if I call this theta 2, then in the picture, that's like right here, which is the same as over here, right? So this is theta 2, and then just, this is a right angle. So if I just look at this triangle, tangent of theta 1 is opposite over adjacent. And then tangent of theta 2 is opposite over adjacent. Okay, so then you can just punch in the calculator and then you know the angles. And then just looking at the picture, clearly theta 1 is larger, right? Theta 1 is larger than theta 2. Okay. Now, what do we do now? Sum forces in the x direction, y direction, and then we can sum torque, right? So Newton's second law for rotation. Okay, so in the x direction, we got the x component of that, negative t1 cosine theta 1. The x component of this, t2 cosine theta 2, equals mass times acceleration, but nothing is moving, right? So again, this is static, so 0. It's great, right? We can just put a 0 right there. Okay, in the y direction, okay, the y component of this, t1 sine theta 1, the y component of that, t2 sine theta 2, and then the weight equals 0 because static equilibrium. And then we can sum torque about anywhere we want. If we sum torque about over here, then the torque from this about this point is 0. The torque from this about this point is 0. The torque from this about this point is 0. So this torque equation really doesn't help us at all. So we don't even need to write anything. So I'm just going to erase it. Okay, so here we go. What are we looking for? Which string? Okay, so which string has more tension, really, is what we're looking for. So from these two equations, let's see. So from equation 1, already I can write this relationship from 1. There's this relationship t1 cosine theta 1 equals t2 cosine theta 2. Okay, and I already know that theta 1 is larger, right? Just look at it. So then cosine of theta 1 versus cosine of theta 2, which is more? Like this, right? Maybe just think about that for a minute. For example, what is cosine of 0? 1, right? What is cosine of 90 degrees? 0, right? So since this angle is larger, cosine of this angle has got to be smaller. So let's just use our critical thinking skills, right? So let's look right here. If this is smaller and this is larger, then this has got to be smaller and this has got to be larger. Right? So definitely T1 is more. The tension in this string is more. So that's going to be the first one to break, this string. Okay, so that's this question right here. That's done. How much mass do you need to add until it breaks? Okay, so how do we do that? Let's keep track of our unknowns. So we know at most the string can support 2.8 newtons, which is, this string is the one that's going to break. So that's 2.8 newtons. So what's unknown? T2 and the mass. Okay, because T1 is going to be 2.8 newtons. So look at this. You have two equations, two unknowns. How do you want to solve it? I would write an expression for T2. So from equation 1, T2 is T1 cosine theta 1 over cosine theta 2. Right, and then we can take that and plug it in right here into equation 2. Right, so equation 2, T1 sine theta 1 plus T2 sine theta 2 minus mg equals 0. And T2 is right here. T1 cosine theta 1 over cosine theta 2. Okay, what's left that's unknown? Only the mass. Right, so then it's just simplify a little bit. I would take this, move it on that side of the equation, and then we can factor a little bit. T1 sine plus cosine like that equals mg, and then just divide both sides by g. And there you go. Okay, let's try another example. Okay, so here there's some kind of meter stick with some weights hanging on it, pivoting on some fulcrum. So what's the first thing we do? Free body diagram. There's the meter stick. It has weight. So the weight, right here, right? So that's the weight of the meter stick is acting at its own center of mass. So I'll just call it mass of the stick times g, which is 150 grams. Okay, now there's these hanging. So there's M1 over here, M2 somewhere over here, and then there's one on the other end over here, M3. Okay, and then it's supported by this fulcrum, so there's going to be some kind of normal force here from the support, the fulcrum support. And there we go, there's our free body diagram. Next, what do? Pick coordinates. So I'll pick coordinates however I want. And you can put the origin wherever you want. There's no wrong choice. Okay, so now what do we do next? Some forces, some torque about any point you want. Okay, so let's get started. Some forces in X. Oh, there are no forces in X. Okay, so we don't really need to write that. There's nothing happening in X. So Y direction, we got minus M1G minus M2G minus mass of the stick G plus the normal force minus M3G equals, this is in static equilibrium, so we get to just put a 0 right here. That's nice, right? Enjoy it while it lasts. Okay, let's sum torque about somewhere clever. And what do I mean by somewhere clever? What is known and what is unknown? Let's look at what we have here. M1, M2, this is known, this is known, this is known. So the only unknowns, the normal force and this mass 3 over here. This normal force and mass 3 over here. Okay, so to be clever, we should sum torque about somewhere to get rid of one of the unknowns. If we sum torque about, for example, here, then there's torque from this, 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 and this, two of which are unknown. If we sum torque about here, then there's torque from this, 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 and this. Only one is unknown, because there's no torque from this force about this point. Then if we sum torque about here, then there's no torque from this. There's only torque from this, 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 and this. Only one of which is unknown. So either of these would be clever choices. Okay, so I'm going to sum torque. I'm going to pick over here, about the end about the end. Okay, so there's torque. If x is here, y is here, z would be this way, out of the page. So counterclockwise would be positive. So there's torque from this. So that's 1 meter and 1g. There's torque from this, which is 70 centimeters, 0.7 meters, m2g. There's torque from here, so that's half a meter, so plus 0.5 mass of the stick, g. And then, how far is this? 30 centimeters minus 0.3 meters times the normal force equals, this is in static equilibrium, right? So we get to put a 0 right here. That's nice. Okay, let's keep track of our unknowns. Right here. Okay, so look at this. You have 2 equations, 2 unknowns. Which one do you want to solve first? Solve this for n. Got it. Plug it in right here. Solve for m3. Done. Okay, one more example. So it's kind of a longer video, but we got a bunch of examples in here. Okay, so there's a ladder leaning against the wall. Okay, so what do? Free body diagram, as always. All right, what are all the forces acting on the ladder? So it's touching the ground, so there's a normal force from the ground. It's touching the wall over here, so there's a normal force from the wall. The ladder itself weighs 400 newtons, so at the center of mass, the weight of the ladder, 400 newtons. And the wall is slippery, so there's no friction, but there is friction with the floor. So which way is it? The ladder would like to slip this way. So there's got to be friction opposing the motion. And then in this particular example, static. Okay, so there's the free body diagram. Let's pick coordinates however we want. There's no wrong choice. Wherever you want to, whichever direction you want to make your coordinates, whichever origin you want to choose, totally up to you. Okay, what do we do now? Some forces, some torque about somewhere clever. Okay, so in the x direction, we got that friction minus the normal force against the wall equals, this is static, so we get to write 0. How nice. Okay, y direction, normal force from the ground, the weight of the ladder, and then equals 0. Right, now, what's, okay, see this static friction? At most, it's going to be mu s times normal force. Which normal force? This one. Right, and then we, oh, that's what we're trying to find. Okay, so that's an unknown. This is unknown. This is unknown. This is unknown. Okay, so these are all our unknowns so far. Actually, right here, we can solve that immediately, right? So the normal force against the ground is 400 newtons, right? So that's done. So then the only unknowns left, this and this. So let's be clever. If we sum torque about over here, there's going to be torque from this, this, and this, 2 of which are unknown. But if we sum torque about here, then there's torque from this and this. Only 1 is unknown. If we sum torque about here, then there's torque from this, this, and this. Only 1 of which is unknown. So I'm going to sum torque about over here, the bottom of the ladder. Okay, so the bottom of the ladder. Okay, so torque from about here would be, from the weight is, see this lever arm right from here to here? So that distance times W. Oh, we don't know that distance yet. No problem. Here's the ladder. This is 53 degrees. The hypotenuse is 5. So if I call this like base and height, right? Then sine theta equals opposite over hypotenuse. So the height, so I'll draw a different color, right? So here to here is 5 sine 53. And then base, cosine theta equals adjacent over hypotenuse. So that means here to here is 5 cosine 53. Okay, so we know these values. And then this is at the center, right? So from here to here would be, and then see, this would cause a torque going this way, which is in the negative z direction. So negative 5 cosine 53 over 2 times W, which is known. Okay, now the torque from this, see this lever arm right here? And that would cause a torque going in the positive z direction, plus 5 sine 53 and W equals 0. Okay, so what are the unknowns? Right here. All right, so look, take a look, right? Solve this for the normal force against the ground. That's done. Solve this one for the normal force against the wall. That's done. Now you know both of these. The only unknown left, mu s, the coefficient of static friction. Okay, so give all of these examples a try and let me know if you have questions. I'll see you on the next video.